ReAct can waste calls by replanning every step, while plan and execute can lock into a bad plan. We'll implement both loops and choose by task shape, cost, and recovery needs. You'll walk away with a setup that chooses the right control loop from task shape, tool cost, and recovery needs. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Agents like ReAct and plan and execute show up whenever a model must act through tools or services. The real question is control. Do you let the model probe and react after every move, or do you give it a full plan and run the steps straight through? In practice, teams decide by three things: how brittle the actions are, how costly tool calls are, and how easy it is to recover when something times out. The right choice reduces pointless calls, keeps side effects predictable, and gives you a clear signal when a step fails. Think of it like two helpers. One checks in after every action and can pivot when things go sideways. The other follows a checklist and is fast when the checklist actually fits. Flexibility wins when the job is brittle. Consistency wins when the sequence is cheap and predictable. Which helper to use depends on task shape, tool cost, and whether you can undo mistakes. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We will build a tiny decision frame that compares a fixed plan against a ReAct loop, measures call costs, and enforces a safety guard. The build is simple, so you can see the signals that matter when choosing which loop to run. Now let us create the smallest plan that still shows the choice. This snippet defines the smallest task shape before choosing an agent loop. Engineers often skip this step and jump straight to a control pattern. But the plan already tells us something useful. There are two intended actions and one explicit recovery concern. The variable plan is intentionally simple because plan and execute starts from a known sequence, while ReAct keeps room to respond between actions. The snippet prints the planned step count and the named risk, so you can see the baseline we will reason about. That visible output gives a concrete baseline for comparing cost and recovery behavior in later steps. We now need a working ReAct-style loop that actually exercises recovery and produces a trace of what happened. This example runs a ReAct-style action observation loop over a tiny tool map. Our real app would call external tools here, but tools keeps the recovery behavior easy to see on screen. The loop writes every action and result into trace, so when lookup policy returns timeout, the next action can still search FAQ and stop after finding refund information. That trace is also the start of incident-style debugging, because you can see what was tried and why the loop stopped. The output shows the number of calls and the fallback action that recovered the task, which demonstrates how an adaptive loop can save a failing execution. With a recovered trace in hand, we can compare expected costs for the two approaches instead of guessing. This code ranks ReAct against plan and execute using a small cost model. ReAct has the recovered trace from the previous step, while plan execute follows plan exactly and looks up each action result. The penalty dictionary represents extra reasoning or replanning overhead. So costs combines tool call cost with that extra control loop cost. Increasing replan cost makes adaptive loops look more expensive. Lowering it makes recovery flexibility easier to justify. The output shows that the fixed plan is cheaper under this narrow cost view, which is useful, but not the whole reliability story. Cost alone is not enough. We must prevent dangerous side effects during execution. This snippet puts a guardrail in front of the execution queue. Cost is not the only production concern. A loop that can recover quickly still needs limits around side effects. The allowed set keeps ordinary read or draft actions, while send refund is filtered into blocked before anything runs. This pattern works for both control loops because it protects the boundary where tool actions become real operations. The output shows how many actions were blocked and how many safe steps remain, which is the kind of counter you would want in monitoring and audit logs. Finally, we combine these signals into a compact decision that chooses which loop to run. This code turns the trade-off into a tiny baseline decision frame. The fixed plan contains a timeout-prone action, so needs recovery captures whether a rigid plan is likely to need help. The if block chooses ReAct only when recovery is needed, and the adaptive path still fits budget. Otherwise, it falls back to the cheapest winner from the ranking step. Then, run and status give a compact operational result: which trace was used, whether it avoided timeout, and how many calls it took. The output shows the selected loop and health signal, tying task shape, cost, and recovery into one visible decision. This toy decision frame maps easily to a real customer support workflow. Replace the tiny tools with your ticket API and a knowledge retrieval service, and use the same decision signals to choose whether to run automated replies or route to a human. The same monitoring counts and blocked action guardrail scale to real operations. What this is: a practical decision frame that compares adaptive ReAct and fixed plan and execute by task shape, cost, and recovery needs. When to use which: pick ReAct for brittle interactions that need recovery, and pick plan and execute for cheap, predictable sequences. One caveat: raw cost comparisons can favor fixed plans even when reliability or human time matters, so include recovery and side effect metrics. For a concrete next step, tune the control knob replan cost while running a dataset of real tickets, so you can find the breakpoint where adaptive recovery justifies extra calls. That single parameter will quickly reveal where ReAct becomes worth the price. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.